On September 28, the European Defence Agency organised the final meeting of the Pylon project, which focuses on the revolutionary concept of the electromagnetic railgun, EMRG, a future additional artillery system with the potential for significantly higher projectile velocities. In April 2021, with funding from the European Commission under the Preparatory Action for Defence Research, it focused on the main research topics being studied under the Pylon project, and the results obtained for each of the three components of the EMRG railgun: the railsatran, the hypersonic projectile, storage and conversion of electrical energy. All 7 partners from 4 European countries who worked together on this study agreed that significant progress had been made in 3 key areas of electromagnetic artillery. This progress lays the groundwork for the future of advanced electromagnetic weapons. The achievements in the Pylon project provide a solid basis for the next phase called THEMA, Technology for Electromagnetic Artillery, launched under the European Defence Fund. The goal of THEMA is to prepare for tests of an electromagnetic rail carrier on a test site by the year 2028. The study includes comprehensive scenario definition for the EMRG system, which was developed in close collaboration with end users during the initial phase of the project. Based on these scenarios, high-level operational and technical requirements for the EMRG system and its subsystems were defined. With these requirements in mind, the Pylon project looked into the EMRG system in detail, researching and designing its 3 main subsystems, namely the electromagnetic rail launcher, the energy conversion system and the hypervelocity projectile. The research was carried out using analytical and numerical modeling, and was supplemented by laboratory tests and experiments in the open field. The scale-up potential was assessed for each subsystem and supplemented by a theoretical and experimental electromagnetic compatibility (EMC) assessment. Later stages of the project addressed systems engineering aspects, and developed integration concepts for both naval and land-based military platforms, leading to proof of concept. Finally, a roadmap with manufacturability in mind. Challenges that were identified in Pylon was developed, thus indicating a realistic way to mitigate the technical risks on the way to an operational EMRG. The implementation of Pylon was guided by 4 key issues. The design of a high-velocity projectile that can be launched by an EMRG. Determination and design of the most suitable energy conversion system for EMRG. Inclusion of requirements for electromagnetic compatibility at all stages of development of EMRG, power supply system and projectile, as well as the possibility of installing the EMRG system on a European-class vessel or a land platform. In addition, the Pylon project explored different energy supply ideas, such as capacitive and inductive energy concepts. Based on the results obtained for each of the 3 EMRG components, important findings were reported at the culminating meeting. Critical components of the railstran launcher, which were exposed to extreme heat and high-speed friction, were protected by special wear-resistant materials, which significantly extended the life of the railstran barrel. The project also developed a hypervelocity projectile concept for speeds up to Mach 6. The performance of the projectile concept was extensively evaluated at Mach 5 through wind tunnel experiments and computer simulations. In addition, the Pylon project explored different energy supply ideas, such as capacitive and inductive energy concepts. The capacitive system demonstrated a 25% increase in energy density under specific operating conditions. Another promising solution, the XRAM inductive energy concept, has demonstrated potential for efficient magnetic energy storage, and work is ongoing to address the technology challenges at the maturation stage, the THEMA project.